Welcome to this video, which is part of a series on propositional logic. This video explains propositions which express complex truth relations. The last video dealt with propositions which express basic truth relations. If you have not watched that video, I suggest you do so now. If you have not watched the videos on truth relations, you should watch those videos before these. And if you have not watched the videos on the method of loci, which is a method of memorization, you should do that before you watch any of these. In English, we express biconditional propositions with the connective if and only if, or sometimes less formally, just in case. You can use biconditionals for both equivalent and contradictory propositions. For memory mention image of a biconditional, I use a double pointing arrow. With a conditional, a single arrow shows that the antecedent affects the consequent, while with biconditionals, the component propositions are sufficient for each other and they're necessary for each other. So I use a double pointing arrow. As mentioned, we can use biconditionals to express equivalence. Recall that equivalent propositions are propositions that are sufficient and necessary for each other. Equivalent propositions are frequently used in philosophy and other fields, such as mathematics, to provide definitions. For example, figure A is a square is equivalent to the proposition figure A is an equilateral, equiangular, quadrilateral. That is, figure A is a four-sided figure with equal sides and angles. Another way of thinking about equivalence is that a biconditional is a conjunction of conditionals such that the component propositions are sufficient for each other. Thus, for P and Q, we would say if P then Q and if Q then P. Since the propositions are sufficient for each other, they are necessary for each other. Thus, they have matching truth values. Here are three equivalent propositions. The first is a biconditional using the traditional if and only if formula. It is also an instance where a biconditional is used to provide a definition. The second uses the less formal just in case. The last is simply a conjunction of the conditionals. All three of these express equivalence between P and Q. Thus, all are acceptable when trying to express equivalence. For a memory mention image of biconditional, we have our double pointing arrow. Since a biconditional expresses equivalence, we have our two assertions. So we have our P's and our Q ball for P and Q. Thus, this represents P if and only if Q. We have looked at equivalence. Now let us turn to contradictory. Recall that contradictory propositions are propositions that are contrary and subcontrary to each other. Thus, at most one is true and at most one is false. Another way of thinking about this is that they have opposing truth values. Now, we could express two contradictory propositions by using the disjunctions discussed in the last video, but that's a little awkward. For a shorter approach, we use the biconditional, but one and only one of the component propositions is negated. Thus, if P and Q are contradictory, we would express this with P if and only if, not Q. It does not matter which component proposition is negated to express contradiction. We could also say not P if and only if Q. Here are some examples of contradictory propositions expressed with the biconditional. In the first case, we have the proposition this number is odd is contradictory to the proposition this number is an integer that can be equally divided by 2. To express this, we use the biconditional and negate one of the component propositions. So we have this number is odd if and only if this number is not an integer that can be equally divided by 2. In this case, the second component is negated, but it could just as easily have been the first. Stylistic and contextual considerations will likely decide this. The second biconditional is actually a little more controversial. Many would claim that a forced act is contrary to a free act, but not necessarily subcontrary. However, I wanted to show an instance of a plausible pair of contradictory propositions without relying on mathematics. For our memory mention image of contradictory propositions expressed by biconditional, we start with a double pointing arrow. Next, we add our P's and our Q ball. Now the Q ball has a not over it to represent its denial. Thus, our image here represents P if and only if not Q. Keep in mind that P could be negated instead of Q, but we will stick with this for now. At this point, you might be wondering about the other two complex truth relations, impossible and absolute. Well, these really aren't best expressed with a connective as with the rest of the complex propositions. These are better understood as arguments, and pretty complex ones at that. So we'll wait for another video to deal with them. Here are important terms for this video. Make sure you memorize these and be able to provide definitions for these off the top of your head. This will help you master philosophy and just about any other intellectual endeavor for that matter. Well, that's it for this video. Next, we'll begin looking at actual argument forms. Stay tuned.